And there are various methods to calculate stress intensity factors. Those are analytical methods, numerical and experimental methods. And for stress intensity factor solutions are available not only for idealized geometries, such as infinite planes or half planes, but also for different types of specimens that are actually used in different tests or experiments. And I'm going to show stress intensity factor solutions for some of the available stress intensity factor solutions for different types of geometries and specimens. We have talked about this. That was our primary problem. An infinite plane containing a crack of length 2a loaded biaxially with equal stresses, infinity. Westergaard method has been applied, and inverse procedure is described, and in the end, we have shown that stress intensity factor, strength of singularity, at both crack tips is sigma times square root of pi a. And in a similar manner, for unequal stresses at infinity, stress intensity factor is the same. And for this problem, a crack loaded by concentrated splitting process, we used Westergaard functions to calculate stress intensity factors at A and minus A. These are sample results for some idealized geometries, infinite plane, remote loading, and there are powerful analytical techniques to solve these problems. But there are other methods as well. Some of the methods are written here. Westergaard technique is a special case of general complex potentials approach. Another effective method in solving crack problems and analytical methods, integral transforms or singular integral equations. Computational methods are most of the time used for complex geometries and loading conditions or material behavior. One of them is finite element methods. The other is boundary element methods. Experimental procedures are also available. Strain gauges. Strain gauge method is basic method. There are some other advanced method as well, like caustics, photoelasticity. So it's possible to generate solutions for more complicated geometries or for certain specimens that are used structure toughness testing. And these solutions have a common feature. They are written in this form. Beta times sigma times square root of pi a. Now recall that sigma square root of pi a is the solution for infinite plane. For bounded geometries, this is modified by including a so-called geometry factor beta. Beta itself is a function of crack length, and it is defined or calculated for different types of problems. We can have a look at some of these cases. The first one is an edge crack now. It's not an internal crack, it's a surface breaking crack. It has only one tip. And its length is shown by A. Our stress intensity factor can only be calculated at this tip. So under mode 1 loading, numerical methods, techniques can be applied to find a stress intensity factor for this problem. This is 1.1215 sigma squared of pi a. Beta is simply a constant. That's a numerical, irrational number, but it's rounded off here. 1.1215 as a reference result, stress intensity factor for this case. Now, problem of practical interest. Again, we have an internal crack, but it's now in a finite width plate. It's not an infinite medium anymore. It has a certain width. It's W. Total crack length is 2a. Stress intensity factor is written as beta sigma squared of pi a. And these are found by singular integral equations or by computational methods. Beta, there is no closed form result for beta now, but this is a curve fit, polynomial type of fit. Cubic polynomial is fit. Beta is 1 plus 0.256 a over w plus other terms. Therefore, this depends on a over w. And w affects the stress intensity factor. Therefore, K1 can be calculated numerically if A, W, sigma are all given. Another suggestion, a simpler curve fit. Square root of secant pi A over W. W now affects the outcome. And mod 1. Another case is the case of an edge crack in a finite width plate. Numerical procedures, finite element method, or single integral equations may have find this stress intensity factor, mod 1 stress intensity factor, beta geometry factor, a curve fit suggestion for beta or geometry factor. Again, as A over W goes to 0, we recover the result for an edge crack in infinite plane, in semi-infinite plane. 1.12. Reference material contains certain geometries for cracked specimens. For example, these specimens are used in fracture toughness testing, in actual testing of materials. Commonly used specimens in fracture toughness testing. We will talk about these. This is a compact specimen. It's a complicated geometry. Now, there are notches here, crack, width, this length is W, height is 1.25, and thickness. And 3D analysis is required for modeling of these. What's the stress intensity factor here? This shaped compact specimen is produced from cylindrical specimens used in fracture toughness testing of different types of materials. Band specimen, simply 3-point band specimen, or here it's referred to a single edge notched band specimen. You can see the details regarding the geometry, and crack length is a, what's the stress intensity factor for this case? These do not lend themselves to analytical solutions. Analytical solution is not possible. Numerical, three-dimensional, and computational analysis are required. Different types of specimens. And for all cases, or these cases at least, this table gives expressions for stress intensity factors in this form. K1 mod 1 stress intensity factor, V square root of W, over P. This is given as a function f of A over W. This function is given here. A curve fit to numerical results. And if the parameters are given, B, W, P, A, crack length, etc., you'll be able to find the stress intensity factor for these specimens. And additional specimens, tension specimens are given here, moment loading. They are all available here, and you may be asked to use these. We will later talk about compliance of the specimens. Crack length has an effect on compliance. Plasticity analysis in later chapters and final part. Next week, I'll be talking about three-dimensional analysis and fracture mechanics, or results obtained through three-dimensional analysis. They are related to semi-elliptical cracks. This is a semi-elliptical part 2 crack. A 2D solution will not be applicable in this case. Fully 3D solutions, numerical solutions are required. Semi-elliptical crack. And cylindrical bodies, part 2 crack. There's true crack in this direction. Now, it's not fully circumferential. And that's a part 2 crack, a semi-elliptical crack in a cylindrical body. Well, these are, we'll talk about these type of problems as well. They require three-dimensional solutions. Next week, we will be considering these cases.